Okay, hi everyone. In this session, we are going to discuss a couple of binary search tree concepts. Okay, so hi Shrikant, hi Venkat.
Hi, hello, sir.
Hi, Suresh.
Okay, so as I said before, just I will give a brief intro about the Yes Mentor. What is Yes Mentor? What we are doing, and what is our motto? Okay, so let me share screen, and then we will jump into the actual topic. Okay. Okay, can you see my yeah, OneNote, right?
Yeah,
Yes.
Okay, just I'm going to discuss. Yeah, this is what the intro actually. I help IT job seekers and understand basic concepts. I will try to help them whoever have trying to understand the concepts, the basic concepts of data structures and coding. I will try my best to help them. And here is the Yes Mentor that I'm saying. So Yes Mentor is I'm active mentor of S Mentor NGO, which is actually started in India, but now they are establishing here as well in US. And It is basically a group of industry experts in various fields and driven with an objective to bridging the gap between the college students, and the corporates, right? So, however, we can help the students to make them, ready for the, corporates and easy how they can get the jobs, right? So that kind of gap. So they have, the normal skills of academic skills, then we are trying to give more industry kind of awareness, how to succeed in interviews and how to get into, once you get into the interview, how to, once you get into the job, how to get to the next levels. It's a mentoring organization of, we have around 20 25 plus 25 mentors are there. We are trying to get this kind of awareness, and a lot of people in India, in Hyderabad, some of the mentors are going to the colleges and other organizations presentations. They are going and helping the students. So they will offer, and we are also planning this a mentorship program for 8 to 10 weeks, so that one-on-one kind of thing. So every it's kind of close guidance, and we will pair one mentor with one mentee, and then they will go on a journey of 8 to 10 weeks, and they will come up with a plan. Okay, what you want to learn, or what kind of guidance you want, and they will assess and they will provide that guidance. Okay, that is the main motto of that organization. Let me just try to show uh, the website. I just want to showcase. Here is the one. Okay, mentoring website here, S Mentor, and they can go ahead and anybody whoever wants, they can go ahead and start a they can sign up for the mentorship. It's in Hyderabad right now. We are putting in US as well. So it's a global organization, non-profit, so free of cost. The lot of industry experts are ready to help. Upcoming students and upcoming generation, and whoever want to get into the mentorship, whoever looking for mentorship. Okay, lot of areas they are giving. Okay, life coaching, management, entrepreneurship, or even technology aspects. Okay, that's about small intro about S Mentor. Please share with your friends and families. Okay, to get the awareness.
Sure. Thank you,
Cool.
sir.
sure.
Thank you. So now we will jump into today's topic. I am trying to give some weekly sessions. So today, last week, we discussed more on the data, like tree data structure. We discussed about trees, binary search trees. So you got some idea, right? Srikant, last week we discussed about how to find out a tree is a binary search tree or not, right?
Yeah.
So this week concept is like this. So let's say we have a binary search tree. This is number 6 here. This is what we are trying to solve here. Binary search tree provides a better mechanism to find the element, right? So that's the main purpose. The main purpose is to searching the element faster compared to normal tree. And that's the first how to find an element, a small algorithm. So if you might already practice it before, it's kind of refresh. If not, we will come up with that algorithm, and we'll go through that. And the next one is how to insert an element, because just think of binary search tree. Let's say you want to put all of your employees. Let's say we have a company and we want to we are always doing the search of a particular employee object for doing some purpose, right? Some kind of operation. But in that situation, we will what we do is we will use a binary search tree for easy searching, right? So now you do that. Now another new employee joined. Okay, how can you insert new element? Because you don't want to construct the entire tree again, because that processing, a lot. So how can we already have a tree, just a new object we have to insert, so it has to go to the right position based on the value, right? So how to do that? So how can we write a small algorithm which is efficient and which will insert element in the correct location? That's the second. And the next one is delete. The obvious reason, like if let's say a particular employee resigns, so you need to remove that object, right? So how can we delete? So these are the basic operations. But in order to delete, it is a little tricky, because if any tree, any node, if you delete, you have to manage its children, right? Let's say you can think of as an organization with employees. If you are, let's say one of the manager resigned and he got another job, he is going out. What about the people under him, right? You need to assign to someone in a proper way. In the binary search tree, we have that formula, right? So we need to make sure after deletion of the node, rest of the node should follow the same pattern, the one we discussed before, right? All the left nodes, this is the binary search tree formula, right? So basically all the left descendants less than or equal to value of the root, and the value of the root is less than all right descendants. This must be true for each node in the tree, right? That is the main purpose here. So even if you delete, it has to satisfy that condition. Even if you insert an element, it has to satisfy that condition all the times. Because why we need to satisfy that condition? Because it will help us to find the element faster, isn't it? Right? So
Yes, sir.
yeah, so that is the main purpose. So but the deletion has the main, as I said, deletion is a little bit trickiest than insertion and finding an element. The reason is deletion involves the management of the descendants. If you delete anything, you have to manage the rest of the, you need to shuffle the tree, make sure it is in a correct order. That is what we call in order successor. We need to find the in order successor, and then we have to attach. So I will go through that in detail. So let's start from the simple one, the finding element, and then inserting. These two are simple, and then we will come to this number 3 and 4. That is the plan today. So and interrupt me anytime. So any question, just treat this as just a conversation rather than a big session or anything. Okay, just something I just practiced. I'm just sharing.
Sure.
Okay, let's start with a small example tree. I think I have here. Just let me get into this. Okay, now can you see the online GDP site here, right?
Yes.
Yeah, this is the sample I created. So we can use this sample. Okay, I'm also using some whiteboard here. Okay, let's take here. Yeah, let's take the similar tree. We have 15 there. I will try to draw similar tree. Okay, and 17 here, and we have 16, and we have 18. Okay, let me put big one. Okay, so now let me put the numbers. So we have 15, right? 15 here, and 3 here, and 2, 14. So is that the tree what we are looking on the left? Is it binary search tree or not?
Yes, it is a binary search tree.
It is binary search tree, because all the right side of 15 are greater than 15, and all the left side are less than 15, and the same formula applies to any node. Let's say 17. See, 16 is less than 17, and on the right side 18, which is on the right child, greater than 17. So right now it is satisfied our binary search tree rules. Okay, now our intention is to insert an element. So how to insert an element? So let's say le- le- we have a tree here, but assume that there is no tree. Just to come up with another small assumption that you need to construct a tree. There is no tree. If there is no tree, if I'm saying like, okay, please add a node with value 12, I'm just saying, okay, there is no tree at all. What do you do? If there is no tree, you simply create a node, okay, and put the value 12 and return that is the root of the node, right? If there is no tree, this is the first element of the tree, isn't it?
Yes.
Now that's a case number one. There is different possibilities, right? So inserting a tree means you can think of as, first possibility is, okay, there is no tree existed before. That means root is null. The first basic condition, root is null. So there is a possibility like the inputs are different. This kind of you can think of as a test cases, right? So I'm saying there is a tree available, and I'm saying please insert a node with value 12. But the problem here is that I'm saying a tree with a node. So tree could be null. So there is one case, test case is the value of the root could be null. That means there is no elements inserted yet. That's the number one first case. So what you do is insert the node and return the root. You're done. You inserted a, because there is no nodes, you inserted a node and you return that as a root of the tree. Now number two is, there is another possibility that, let's say a tree with value 12 is there. Now I'm inserting you another value 11. So the second case is, there is a node, okay, and you need to insert another node, okay. So now how the 11 is going to be inserted in this tree? There is a 12 is the root, okay. So r equal to 12. So now where are you going to put the 11?
Right hand, left hand side, sir. So 11 is less than that 12, so then we can put it in the left hand side.
Left child, right? So you
Yeah,
are going to add 11 as left child of 12, isn't it?
yeah,
Right. So if you look at essentially what we are doing here is, step number one is we are creating a node called 11. That means node, I think last week we discussed about it, right? Node is structure that we create in order to store the value and in order to store the left and right nodes of a particular node of the tree, right? So we'll create the node object and we'll put the value 11 in it. And now what are we going to do is we need to attach that to the 12. So what is that attaching means? Attaching means basically based on the value, if it is 11, which since it goes to the left side of the 12, we will update the left address of 12, isn't it?
yep,
So r dot left equal to 11. If the value, if I say 17, if I'm saying no, not 7, not 11, if I am asking you to add 17, then you don't add at the left side. So you add, this, you update the right, basically, you add here. That means you update the right address of the node, isn't it?
yeah,
So essentially, this node is not changing. You are creating a node, okay, you are creating a node, but you are updating the existing node. That is the main logic here, basically. So if you are inserting a node in the tree, you are inserting a node in a tree, so you are essentially just creating a new node with the value, but you need to update one of the node in the existing tree. One of the node, because it could, you need to find what is the exact correct parent, isn't it? Right?
yes,
So you need to find the correct parent, and then either you need to add the new node as a left child or right child, isn't it? So we are updating the existing node of the tree. That is what the insertion means, right?
yeah,
So the one thing is, most of the algorithms in the trees are recursion. So that is main problem of your understanding. Like it's not a straightforward, it's a recursion code. Okay, every algorithm of the trees probably has a recursion. So that's the reason I'm trying to explain in a very basic example. So first scenario here is without any nodes. If there is no nodes, you just create a node and then call it a day. This is the root written, this is the root done. The second scenario is a node with a single value, a node with the only one, a tree with one root. Okay, then you just add either left or right. Okay, you added 17, let's say if it is 11, you added here, 12 is here. Now if I am asking you to add 19, then what you do, you start with 12. So 19, you know, because it's a no tree is very simple, very small, we can see, with our eyes, and we can see 19 will go on the right side. But if the tree is really big, the thousand elements or million elements, you need to traverse left, right, left, right, left, right, and find out the exact location, isn't it? Right? And then you need to find the correct route, and then attach this 19 to the proper route. Correct? So
Yes.
now our intention, we will take this 19 and we will start with the route, we will navigate left or right. Our intention is to find the correct um, element, correct element, which is available in the tree, where we need to update the left or right based on the value. Okay, so now how the recursion work is, I don't want to show the code or directly algorithm, I'm trying to explain the way we are doing. So let's say, let's get back to this, right? The big tree here, what we have. So now we have this tree on the left side. Now I'm asking, like, let's say we want to insert 12, we want to insert 12. Okay, so now what we do, let's assume that, the tree is left side we know here, where directly I think you can, anyone can say the answer where the 12 goes here.
For the 14th left.
Exactly. So it's simple. The tree is very small. We can directly say 12 will go to the left of the 14. Now, if I don't tell you the numbers, okay, I just drew a tree without even telling the numbers. There is a number there. Okay. If I say something like this, if I'm hiding the number, there is a number there. There is a number here. How can we find? What we need to do is we need to write an algorithm that will traverse each node, and then find out the value, find out the correct location, right? That is what the intention of our algorithm, because our algorithm don't know this entire tree at the glance. It needs to traverse each node and then find the value. Now we know the tree is here. If the tree is like this, right, if the tree is like this, just 15 and 17, now where the 12 go?
Left of the 15.
Left of the 15, that means 12 just goes here. That means you are updating the 15, you are updating the root node here, right?
Yeah.
But unfortunately here it is not free, it is not free. Here there is a value, here there is a value called 3 here, right?
Mhm.
But how the recursion work is, since there is a value here, since there is a value here, now what I'm trying to do is take this 12. Okay, we compared with 15, take the 12. Okay, 15 is smaller than, sorry, 12 is smaller than 15. Now,
Left side.
left side, what I'm trying to say is update the entire left subtree. Okay, update the entire left subtree. 12 may go here, 12 may go here, or it may go somewhere under the hood, but I don't care. Update the entire subtree. Okay, and whatever the node here, that will be assigned to this one. That means, let's say this is r, right? So r dot left equal to, now do the same insertion algorithm for the left entire entire left subtree. So what I'm trying to say here is, now we are solving the sub problem. That means now initially we are trying to insert 12 in this tree where 15, 17, 3 is there. Okay, 3 is here, right? We have 15, we have 3 on the left side, 17 on the right side. Now we are trying to insert 12. So our initial problem is try to insert 12 in this tree. Now we figured out 12 should not go to the right side. Now 12 will go to the left side. Now the problem is, okay, now here is the tree becomes like this. A small tree. Now the root is 3. Now the root is 3, right? And at 12 we need to insert. Of course, 3 has some other nodes. We don't know yet. Now the problem becomes like a smaller problem where 3 is here, sorry, 3 is here, 2 is here, and then 14 is here. Now you need to insert 12 in this subtree, isn't it?
Yeah.
So basically, we are trying to. This is the recursion. When recursion is always like the we are solving the same problem for the subset of the input, isn't it? So now the problem becomes like 12. You need to insert for the subtree. If I need to really highlight here, this is what I'm trying to say. Initially, we try to insert for the entire tree. Now we are trying to insert for the subtree. Now what happens? Now again, now 3 is greater than sorry, 3 is less than 12. Now what will happen? 12 should go to the right side, isn't it? Now at this point, okay, I don't care, try to put the 12 on the right side here, but update the left of the node here. So here, sorry, right of the node. So for 15 you need to update the left of the 15. For 3 you need to update the right of the node, right, basically right of the 3, isn't it? Based
Yeah.
on the value you are inserting, either you are updating the left node, left pointer, or your right pointer, isn't it?
Yes.
So this is a very fine line I'm trying to explain. So basically, we are trying to make the problem smaller and smaller and smaller. So now what will happen is now, hey, 12 is here. 12 should go to the right of the 3. So we will simply say 3 dot right, whatever the 3 node. 3 dot right equal to, again we call the insert function. Insert. Now the root is 14. Take the 14 as the root and try to insert the 12. So if the insert algorithm is like this, if the insert algorithm has a first one is the root and second one is the value that you want to insert. Okay. So first you start with 15. Okay. Now 15, we want to insert 12 here. Okay. We know the 12 will go to the left side. Now the insert will be like this. Insert of 3 because you going left side. 3 and 12. Right. So again, so 3, now 3 is smaller. So now again we call the insert with 14 and 12. You understand? So basically we will call the same method recursively until it should go to the right place. Now what will happen? Now the algorithm is like this. You just have 14 as a root and you are trying to insert 12. Again, what will happen now? Insert 14 dot left. Now here the 14 dot left, it go to the left side, right? Now 14 dot left is null. What that means? There is no value to iterate. So if the 14 dot left is null, simply you put that the new value there. You got it? So basically we need to iterate or recursively go down. We need to make the problem smaller and smaller and smaller. So now it will automatically adjust. So now what we do is we'll insert the 12 here. Now the 14th left was updated. 3 is right also updated. Of course, it's not updated at this point. It's still pointing to the same element. Even left 15 left address also updated, but it will point to the same value because it's already there. So that's the main algorithm here. I will show the algorithm. So any questions on this explanation? Is it clear? Basically, how we are doing is basically always check the value of the root and the value that you are trying to insert at any point. That's what you do, right? You take the 12 here. Our eyes did like that, 12 we compared with 15. Okay, they should go here. Now 3 and 12 you compared. Now it should go right. Now 12 and 14 you compared very quickly. We worked our brain did this in a fraction of milliseconds. Now we understand, okay, 12 is smaller than 14. Now put the 12 on the left side, isn't it? That's how our brain worked. Within fraction of milliseconds, we figured out, okay, left, left, right, right, and then we figured out. The same thing you need to do in the algorithms. Okay, so this is a straightforward algorithm. I will show that this is a node architect, node format. As I said, node has two things, three things. First one is value, which is integer value, and then left and right. These are two addresses. Very simple format, right? Now, if I show you the insert, this is what I'm trying to explain. Okay. Oh, we forgot to do the find actually. We'll do the find, but insert is the another one. We will first discuss this. So look at this algorithm here, right? So what we do, as I said, we'll put the root here and we are inserting value v. Okay. If the root is null, this is the first case, right? As I discussed before. If the root is null, simple. Create a new node, simply put the value and return that new node. Isn't it?
Okay.
Right? So now the other case here, if v dot v value is value, v means value. If value is less than root dot value, okay, in this case the same thing, right? We want to put the 12, okay. So but the 12 is right. Let me put here, okay. So 12 is here less than the 15, right? So now what we are doing, root dot left equal to, now we are calling the same method insert node with the root dot left. Now we are saying, okay, solve that insertion problem for this subnode, for this subtree, where the value is 3 now, root dot left, and the value is same value. So we are passing the value 12 here, and we are calling the same insert method, okay. And now we are changing the root value in the insert method. Now tackle the problem with 3. Now 3 and 12 will be compared, isn't it? Are you following?
Yeah, yeah.
Yeah, Venkat, I think are you also following or any questions? Let me know.
Yeah, I'm good though.
Yeah.
Yes, yeah, I'm
So
following over there.
this is a recursion, very fine line we are trying to explain. So now let's assume the three was not there. If the three was not there or any subtree is not there, what you do is you simply create a 12 and 12 will be updated as root dot left. Right? That means if the then 12 will be inserted here and that will be the 15 dot left. That's why we are calling root dot left equal to insert node. We still need to understand like why we are changing the root dot left. This is a very fine line trying to explain. Okay. So now in this situation we have a 3. It's not free. We have a 3 here. So now it will go further. Okay. Now the root value is 3. 3 is not null. Now we'll compare. Is 12 less than 3? No. 12 is not less than 3. So basically here value is 12. Now it will come to the right. So now value is 12 and root dot value is 3. Now it will come here. Okay, now 3 dot right equal to insert node. Now we are going to call the insert method with the 3 dot right, which is 14. Right? Now what will happen? Now the value root becomes 14, which is not null, and now value is 12 less than root dot value. Yes, value is 12 and now 14, right? So the root dot value is 14. Now we are saying root dot left equal to, root means 14. 14 dot left equal to, we'll call the method again, insert root dot left and value 12. Now this is the final point. If you say root dot left, what is the value of root dot left here? For 14, what is the left?
True.
12.
No, you haven't inserted 12 yet. So
Yeah,
it's a
yeah,
null
Yeah.
value, right?
null,
Yeah,
null.
not valid. Yes.
That's why if you call insert node with 14 dot left, which is a null, this base condition will be satisfied. So this will be satisfied in two cases. If there is no nodes in the complete tree, that's a one use case. There is no nodes. There is no 15, no nothing. The entire tree is empty. That is one condition. The other condition is whenever you find the spot, whenever you find the correct spot. Now this is a 14 is the correct spot, and 14 dot left becomes, we are passing 14 dot left. Then what will happen? That there is null value. There is no left for 14. Then we are creating a brand new node and we are putting the 12 in that node, and then we are returning the node immediately. That means we created this 12 and we returned that node. Now the pointer comes here and the 14 dot right will be updated. That means 14, we are establishing that connection. You got it? So 12 will be returned. Now 14 dot left becomes 12. Now root will be written. That means 14 will be written. That means 3 dot right becomes 14. Of course, it's already 14. 3 dot right is already 14. It will create one more time. It's a override the value again because we haven't updated 14. It will be the same thing. Again, 15 dot left becomes 3. So it's a backup, backing up all the levels of the recursion. It's a very simple algorithm, but this is trying to understand. If you understand this whole concept, then it will be easy rather than by hearting, right? It's
Yeah,
really tough to by heart these lines. Like it's easy to by heart, but it's tough to remember. Over the time, you will forget.
yeah, that's true.
So I'm trying to explain like why we are calling with these values left and right. Okay. Cool. That's insertion. So now coming to the quickly, we'll follow the find. Find is almost similar. Actually, I should explain find before insertion. See, look at the algorithm here. Same thing. Root and value find. We want to find a value. So simply, let's say 12. Is 12 in the tree or not? After insertion, it is there. Let's say if I say like 18, 18 was not there, right? Probably, yeah, 18 is there. So how you go? So you compare with 15, since 18 is greater than 15, you go to the right side and you compare with 17, it is also greater than, you go here and you compare. Let's say if I ask you to find 20, you do the same thing. 15, you compare 17, you compare 18, and finally 18 dot right is null, so you say false, right? That's the same logic here. So basically root equal to null, return false. If the root value is null, that means false. In this case, what will happen is the same thing. Like if you go to the 20, ultimately the root becomes null. So, and if the root dot value equal to value that you are looking, return true. Very simple. Like if you want to find 17, at some point, like you becomes root value is 17, you return true. These are the two base cases, true false cases. Now, if the value is less than root dot value, call the same recursion find node with root dot left and put the value there. Otherwise, root dot right. It's very simple, right? You just navigate either left or right, left or right. So, what is the algorithm? Anyone can tell what is the uh, complexity, time complexity of this one?
I think n log n,
N log n or log n? I think
log n,
log
log
n.
n. Because like if the value is less than something, so half of the tree will go away,
Hmm.
and it needs to find it in the remaining half of the tree.
Yeah. So it's a log n, right?
Yeah, log n.
Log
Yep.
n. It's so half of the tree. If you say half of the tree, that is half of the tree, but not half of the elements. That is the very fine line here. So
Yeah,
people will say, "Oh, we have 100 elements. That means 50. Are you going to compare 50 times?" It's not half of the elements. It's a half of the tree because you don't compare every element on the right side. Let's say you are trying to find 20. You don't compare with 16 at all, right?
yeah,
So there is no guarantee that you compare half of the elements. So that's why it is not n by 2. If it is half of the elements, you can simply say n by
yeah,
2, but it is not. It is why it is not n by 2, because you always take the path based on the value of the road. It's not, there is no guarantee that you compare half of the nodes. It will be less than half of the nodes most of the time. That's why it is log n. Log n is less than half of the nodes. So that's why it is way efficient than searching an element in an array. Let's say if the array is not sorted, you have to search each and every element, right? It's an order of log n. So if the elements are million elements, you have to navigate all the million elements in order to find out whether the element is there or not. But here there is an order. Here there is a better way of finding. Okay,
yeah.
that's the main difference here. Yeah. So is this find algorithm is also clear?
Yeah, only one quick question,
Yeah.
sir. Here. So for every binary search tree, either for search, for insert, for delete, all the complexity will be the login only,
I
or
think so. Yeah,
okay,
because
okay,
we are now in and login. Basically, we are navigating based on the value only, right?
Mhm.
So either left or right, always decide based on the value. So you will be able to reach the right value. If the value is always all on the leaf node, it will be log n. So that's a
Okay.
formula to go down all the way to the leaf node. So that's a worst case scenario. Yeah. Let's say if I say, hey, find 17, just two comparisons. You
Yeah.
compare with 15, you compare 17. They're order of two actually. It's like in a constant value. Let's say if you find 15, just only one comparison, root, because you can see that value is root. Those are best cases. But if I say find 16, then you need to do three comparisons, which is log of these n elements, I think. Yeah. So um, so find is easy, insert is easy, but delete is the most difficult part. So let's jump into that difficult aspect of the um, thing, and then we'll wind off. Okay, I try to wind off by 9, but it's always a little bit here and there. We'll go. If you have any hard deadline, let me know so that we will stop there. So now delete node. Okay, so now how can we delete node? How to do the deletion? Okay, let's come up with an example here. Let me redraw actually. Let's so let's see. Let me draw the same tree. Okay, so we have. So in the meantime, let's think about how the deletion works. Okay, let's say we have exact same 17 here and 16 here and 18, right? So now 15 are here, 3 here, 2 and 14. Okay. Now let's assume that you're going to delete 17. What you do in normal scenario, you want to delete 17.
Okay, so in this case, if I want to delete 17, so first we need to check it is having the childs left or right.
Mm-hmm.
And then if we can check and we can delete the parent, and then we need to arrange the uh, subtree with root as well as a left or a child, whichever the possible way. So we need to restructure that tree, that
Exactly.
whatever the subtree.
Exactly. That is the main complexity of delete. Let's say if I say only 15 is there, then you can simply delete that node. If there is only one element, you delete, make it null or whatever. Okay. Now let's say another scenario is a root with single child. A root with single child. Let's say this is A and B for the simplicity purpose. Okay. If you want to delete B, what you do, you basically make the make the A dot left equal to null. Simple, right?
Yeah.
So in this case, let's say we have A and B, and we want to delete A. Let's say we have A here and we have B, A here and B here. Okay. Now you want to delete A. What you do?
We can make it b as a root.
B as a root. Simple, right? So now in the situation, basically in a broader way, if you look here, let's say if you want to delete 15, there are two ways to if you delete 15, there will be very big problem here. Like there will be two subtrees, 3 2 3 4 14 is one thing, and 16 17 18 this is another subtree. You need to make sure they're connected, right? So how can you do this is basically the simple algorithm which is very popular here is you need to find the in order successor. So how to find it, like, let me tell you what is in order. In order. So what is the in order of this tree? Can
In
anyone
other
tell?
like 15.
In order, not pre-order.
Okay.
Pre-order.
16 like if
No,
you if you
I'm saying like not the in order successor. I'm asking, can we do? Let's do all the numbers of this tree in the in order.
okay, 2,
Two,
3,
three,
14,
14.
15,
Yeah, 15 and
16, 17, 18.
18. I couldn't write properly with the mouse.
Yeah, that's
so so basically, you are deleting a 15. if you think of this as a simple array, right? What you do, you basically after 14 you directly read the 16, isn't it? Because
Yeah.
the main advantage of this BST, the binary search tree, is the BST main formula is it will make the in order sorted. If you do the in order, all the elements will be in a sorted order. So now you basically essentially, let's say if you're removing 16, then after 14, 16 will come. That is called in order successor. Okay. But 14 is here, and 16 is here. You don't see any connection between 14 and 16. It goes all the way to here. But that is actually the in order successor, isn't it?
Yeah.
Right?
Okay.
So
Okay.
the main purpose of this deletion is, once the deletion happens, is basically you need to find basically, if you do the in order again, if you do the in order, it should be in a sorted order, right?
Yeah.
So um, people will think, okay, why don't you we put the 17 there? Let's say, just for the sake of understanding, let's say we
Hmm.
just for us understanding, let's say we want to delete 15, and why don't we put 17 here? Let's see if that satisfies our condition.
No.
Why?
16 will be the less than, so it should go to the left of the tree. I think under the for 14, it should
Exactly.
come.
Exactly. That's why that's the problem. So, but let's say if you have 17 here, and then what you do with this one? So, if you 17 is there, you need to put either in the 17th place, you need to put 18 or 16. Let's say you put the 18, and oh
Yeah.
my god, this is really big. I need to remove, reduce this. Yeah, you put the 17 there and you 16 there. But if you look at these two satisfied. This is 18 and this
Yeah.
is 16. But the problem here is the, this is also satisfied, right? So
Yeah.
17 and 18, even if you take these two things, 17 is smaller and 18 is bigger. These two satisfied BST, even these two satisfied BST, because root is bigger and left side is. But if you compare these two,
Yeah. It is
then it
not.
failed. It failed the BST formula.
Yeah.
That is why taking the 17 into consideration, moving the 17 to the top, is a really really bad idea.
Yeah.
When we are started algorithms, we'll simply say, oh, why don't we take, just simply put the if you remove 15, take the right value and put it there. That is the problem. So that the best solution is put the in order successor. But there is another solution is there, anyone can tell, rather than putting let's say, now let me draw the output here. So if you delete the 15, right, what are we saying is we need to put the in order successor. In order successor is, okay, so this one, so we'll put the 16, right? In order successor is 16, we'll put the 16. We don't change anything, we don't change 3, we don't change 2, we don't change 14, right? So 17 and 18, right?
Yeah.
So now the tree is, again, if you move the 16 all the way to here, then it is still BST, right? So
Yes.
this is what we need to find. We need to find the in order successor and put to the correct location. But what about, there is another solution, I think. It is in order predecessor. I think maybe we can put the predecessor also. Let's say, what I'm trying to say is, what about, I'm just thinking loud, can we put 14 also there rather
Yeah.
than
That's
16?
true. Yes, true. Yeah.
Either
Yes.
you need to put the in order predecessor
Or
or
success.
in order successor, because
Oh,
let's say you can't put 3 here, right?
yeah. I
If you
understand.
put the 3, 14 is a problem. Like 14 will come here, then 14 is bigger than 3, which will fail the BST formula. But if you put the 14 here, right, then 3 can be here,
Okay.
right? So either there are two cases. It's not always in order successor. Either you need to put the in order successor or in order predecessor. So very
Okay.
popular thing is take the in order successor and put it in that location. Okay.
Okay.
So now in the put it in the location means, like, basically you don't want to. change the left or rights, right? You basically take this value and put it there. That's how we do in the algorithm also. That's how I saw the algorithm. So it's not like you're re-establishing, you're not moving the entire node from here to here. What we do is basically we will rewrite the value of this node to 16, and now the 16 node is here, right? Now you need to remove this 16 node, the node value 16. So now let's say you took the value from here and put the value here. Now the problem is, now we need to remove the 16, isn't it?
Mm.
So the
Yeah.
problem becomes smaller. Basically, now entire tree is good. Now you need to remove the 16. The initial problem is remove the 15. Now you removed it. You removed the 15 with, you replace the 15 with 16. Now you need to tackle the deletion of that 16. Okay, so that's how the recursion will work. So what I'm trying to say here is why it's so. There is another possibility like this. Let me tell you the example. I think these numbers are not easy for me to explain the scenario. Let's say without numbers we'll draw, without any numbers. Okay. Okay, so now you're going to remove this node. Okay, this we don't know the number. Let's assume the number some x. Okay, you want to remove x. So this is a BST. Okay, and here is a, here is a b. Okay, c, d, something. So what is the in order successor of this x?
C.
Do you think it's a c?
C, B, D, A.
Yeah,
Yeah.
actually, yeah.
Yeah.
So,
Yeah.
but because what will happen is if you write in order, okay, then it will be in a uh, um, ascending order, right? So you write the value here, you write the value here in the normal array. If you write the in order, then it comes a. After
Yeah.
a, it comes this. So if I put the numbers, it might be easy to understand. But what I'm trying to say is this is the in order successor. Let me put some numbers. Let's say you have 17 here, and let's say 20 here. Okay, and 18 here, because that's still BST, right? 21 here. Okay,
Yes.
so
21.
now let me reduce, and let's say here you want to have a 15 here, right? And
Mhm.
8 here, let's 8 or something. And now it could be 25, right? Or
Yeah.
30 here. Is it still BST? Right?
Yes. Yes.
So now you want to delete 15. What will happen? What is the inner successor here? Definitely this one, right?
Yeah. 70.
So after 17, you inserted 20 here. After 20, you inserted 18, comes here, and 21 here. So now it still follows the BST. Now if you move the 17 to here, right?
Mhm.
Then how to replace the 17 value? What is the next value here? In place of 17, what we need
Eight-
to put?
18.
18, not 20, because
Yeah.
the problem becomes a sub problem. Now you need to, in order to remove the value here, you need to find the next in order successor, which is going here and then finding the next one. You need to put 18, not 20. If you put 20 again, it will screw up the BST formula, isn't it? You can try.
Yeah.
So if I put 20 here, if I put 20, if you take this 20 here, you need to put either 21 here, or 18. If you put 21, what will happen? 20,
18.
21, 18 is crossing the limit, because 20 is, all the right nodes of 20 must be greater than 20, right?
Mhm.
So that's the problem. Yeah.
Yeah, that's true.
Yeah. So we are almost done. My daughter's class is about to start. So,
Okay.
but you found the actual logic, right? What we are
Yeah.
trying to do, right?
Yeah.
So now let me show you the algorithm. Yeah. So now let me show you the algorithm, right? This is the complex part of the whole thing. This is where the deletion, you know, works. Here is the deletion. See, look at this. This is the root and this is the value, right?
Yeah.
So this is simple case. As I said, if the root is null, simply return null.
Yeah, that's true.
If the value of the root is, you know, the value is less than root, you are going to update the left for sure, right? We are making the problem smaller again. Look at this. So if the value is smaller, somehow the root value will be either updated or it will you go down, right? This is the same, similar to the insertion. We are doing the same thing. Root dot left equal to, we'll call the delete. Okay, so do the deletion at starting from the root dot left. So now the
Yeah.
root becomes root dot left, and it will call the same function with the same value. Okay, let's say if it is right, if the value is greater than root dot value, you do the same thing. Okay, root dot right, do the deletion, and I want the root dot right should be updated. Now the problem comes here. If we find the value to be deleted, this is the main logic. You found the value. If you want to delete 15 or 16, whatever in the tree, now you found the value. Now this is the, of course I forgot to tell about this. Basically, if the root dot left equal to null, then take the root dot right. If the root dot right equal to null, take the root dot left. This, in order to understand this, let me go back to the whiteboard here. If the root dot left equal to null, okay, if the root dot left equal to null, that means, just a hypothetical example, you don't have this node. Okay, okay, so now in this let's take an example. You want to delete 17. What you do? Root dot left, there is no root dot left. Simply take this 18. There is no need, no problem, right? Because there is no left.
Yep.
You just need to chain. You cut the chain and then you take this, whatever the node you connecting directly to here, isn't it? You are returning that root dot right. If root dot right equal to null, let's say you assume that something like this. You don't have, okay, um, you don't have right node, but you have left node. So now you want to delete 17. What you do? You directly connect. You directly give that root dot left because there is no right. If the right is null, give the left. If the left is null, give the right. But if you have both, the else case means node to be deleted has both left node and right nodes. Then we have to find in order successor of its right subtree. Okay, this is what the main understanding. Like, let me, before if I forget, let me share this with you in the comment section. So whenever you have some time, just glance the logic and see how this works. Okay.
Sir, one quick question.
Yeah.
So after end of this meeting, so where can we get all these links, sir? These share code links.
Yeah, I will forward. Actually, it is in the same LinkedIn. Actually, LinkedIn post it is there. So I'm trying to
Oh,
put it. Okay, let me put it on the meeting. I'm meeting chart. I'm trying to find the meeting chart here. I will also, yeah, I am putting in the meeting chart before I forget. You can copy from the meeting chart and follow the LinkedIn posts. Actually, this Yes Mentor is doing all the publishing aspect, like publishing the meetings and also publishing the links afterwards. Okay, you following the LinkedIn, right?
yeah, yeah.
Yeah, please follow that. So you can definitely, these are all the algorithms I curated, I wrote, and with all the comments and I tested. So it's 100% perfectly working algorithms. So you can go through this. I wrote in C sharp, but you can easily convert in any language you want. I think it will automatically converts. Of course, you can easily understand also. It's just like C kind of language, right? I did not use any of the functions of the C sharp inbuilt functions. Okay, this is just a C language kind of code. Okay,
Okay. Yeah, thank you, sir.
so here is the else case, right? This is the main crucial part of this. This else case will comes if both the root has left and right nodes, right? That is the initial situation here, right? Initially we have left node and we have also have a right node. If you have left and right nodes, our intention is we need to find the in order successor. Okay, there is a separate method we created, in order successor root dot right. So this root node you found, that the found the node to be deleted, But what we do is in order success is always like, um, uh, we say, let's say you want to delete this, right? You will say, hey, starting from this, give me the in order successor. It always goes with the right side and then full left side, right? That's why if you look at this in order successor, we call the root dot right, and we give that to the function. This function will give you the in order successor. I will show you that function is here only. But let's say we found that in order successor. What we do here is we need to take the value from the in order successor and put as a root value. This is the main point I'm trying to understand. So whenever you got 16 here, so after 15, if you want to delete 15 here, right, you need to take this value and put that value here.
Okay. Yeah,
Okay,
root for root. Okay.
now 16 was here. Now you deleted 15. Technically, you deleted 15. You replaced it with value 16. Now our intention, we don't want to have duplicates, right? Now we need to delete this node. Okay. Simply we call root dot right equal to, okay. Root means, okay. Root means the node to be deleted. That means this is the node to be deleted. Let's say 15 is here. Now 15, you replaced 15 with the value 16. Now this root dot right, that means this one, equal to delete node root dot right root dot value. Now what we are saying is root dot value. What is the root dot value? 16. Now we are starting another algorithm saying, hey, take this entire subtree and delete the value 16. So let's assume that this is a unique nodes. Okay, 16 is already here, so there is no 16 in this subtree. Then that 16 will be deleted. Using the same algorithm, you do the same kind of logic. Now the problem becomes a smaller problem. Initial problem is a big tree where 15 is on the root. You're trying to delete 15. Now the problem is smaller problem. You're tackling the smaller subset of the tree. Now the problem is trying to delete the 16. Why we need to call this is, the 16 may have another nodes, right? There could be another big 100 nodes or 200, we don't know, right? Similarly, on the right side you can see this. If you take the value from here to here, what about these nodes? What we do is simply take this subtree, delete the value here. That means it will follow the same algorithm. So now we have to delete the in order successor. So initiate that call. So basically we are going to call the same delete function with that value. Very
Okay.
important. You understand the logic here?
Yeah, yeah, yeah. No.
Yeah. It is very fine line. We need to the I would request whoever is preparing, like whoever is going for interviews, or maybe it's better even if you want to dive deep and how it is really doing it, I will put a breakpoint. That's what I did. This is all algorithms I did couple of years ago. I studied those and I put the breakpoints, and I trying to understand each and every line while you debugging. Oh, this is what is happening. Then you will able to understand clearly, right? So that's the main purpose here. So it's kind of a iterative deletion. Even though you're asking me to delete one value, the algorithm will delete one value and then it will try to delete one more value. Again for 16, again you need to find another in order successor, and again that will be
Yeah.
deleted again. So it's a recursively go. So how
That's
the
it.
in order successor? It's a very simple algorithm. So this is a two lines algorithm. So if you want to find the in order successor of this node, simply go left, 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 all the way to the left, right? So that's the in order successor. So what we did here, you go here 25 and all the way to the left, and this is the last node. That is in order successor, right? Here also same thing. You go right once and then go all the way to the left. That's the in order successor, because this is a BST, right? So if you have the nodes like this, let's say after this is the next node,
Okay.
because all these nodes are greater than this, right? Basically this is how the BST works, right? So that is the in order successor, but this node may also have some right nodes. We don't know, those can be tackled with the another deletion. That's what I'm trying to say. You take the value here and put the value here, and then tackle the deletion of this node, in a different delete node algorithm. Yeah. So here is the find in order successor, and you get that successor. and you copy the value. So this is the algorithm. I think I took from the same CIC, like coding cracking the coding interview book, I think. So if you find any different algorithm or simpler algorithm, let me know. We're always happy to discuss. But that's the deletion part. Okay.
Okay. Yeah, thank you, sir.
Awesome. Awesome. So any questions or any uh, yeah, let's look at the here. Um, let's look at the input here. After insertion of 20, this is the input. It's always like input is always like a small array. So I did a in order printing. So now after deletion of 20, what will happen? 20, if you delete 20, it will be the list. Now if you delete 18, so what will happen after 17? You get the 19. So if you delete 15, right? So 15 the place of 15, you get the 16. And yeah, if you look at the actual connections, that will be interesting.
Okay.
Because we cannot show the connection in the output, right? So we always able to just print the elements.
Yeah.
Cool. Yeah, that's for today's discussion. So maybe next week we will dive deep into the next chapters like minimal tree, minimal binary tree, and yeah, and this is also another thing. Given a binary tree in an array format, right, binary tree traversal algorithms, because right now what we discussed is a simpler and easy to understand structure like this, right, with the pointers, left and right pointers. There is another way to write the binary tree simply using an array. If you put the array in a particular elements in this order, that's a you know if you are sorted array, let's say this is a sorted array, right, you can think of a sorted array as a binary search tree, right? So that's where the algorithm is like right binary tree traversal. So if this is in order traversal, right, but how can we write, if you think this as a tree, how can you write the other traversals, pre-order, post order? That's the question. We can discuss next time. And we can also discuss about the heaps. What is the heap, min heap, max heaps? And yeah, these are the things lined up next week. Feel free to join so that we will discuss those algorithms.
Sure. Thank you, sir.
Awesome.
Thank you, Suresh.
Thank you, Venkat. Thank you, Shrikant, for
Yeah,
joining, and we'll meet again next week. Okay.
Yeah. Thank you.
sure.
Awesome. Yeah.
Thank you.
Talk to you later. I'm
Yeah.
going to
Bye.
stop the recording.